Okay folks, so next up is P1B and keeping homes warm. So I just wanted to make sure we've got a bit of terminology that we're all happy with. So we're talking about energy an awful lot here, and these are the main types of energy that we need to think about. So we can talk about heat energy, which can also be called thermal energy. It's the same thing, so it's just energy associated with the temperature of objects. So objects that are hotter have more energy. Light energy is just what it says on the tin. It's energy due to the light, or the movement of light anyway. Kinetic energy is the energy objects have because of movement or because they're moving. Sound is energy due to transfer of sound. Nuclear energy is energy that's stored inside the nucleus of an atom. Elastic energy is energy that's stored in objects when you change their shapes, when you compress or extend them. Gravitational potential energy is energy that objects have based on how far away from the Earth's surface they are. Chemical energy is energy that's stored due to chemical reactions. So if something has the potential to do a chemical reaction and give out energy, it's got chemical energy. Then electrical energy is just to do with electricity. Now, it's really important that we get really firm in our head that energy can only be transferred. So you can only change it from one type of energy to another. You can't ever destroy it, and you can't create it. There is a fixed amount of energy in the universe, and all we do is change it from one form to another. Now, as a general rule, whenever we do an energy transfer, some of that energy goes towards heat. So we always make a bit of heat. So if you're doing an energy transfer and you think, have I got everything? If you haven't got heat, you've probably missed something out. Okay, so those are just types of energy. So now we need to think about how they're transferred. There are three main ways that energy is transferred. There's conduction, convection, and radiation. So, conduction is where energy is transferred through a solid due to the transfer of kinetic energy between the particles. So basically, I give some of the particles at one end of an object energy and they start to vibrate more. They knock into the ones next to them, giving them more kinetic energy, and that energy gets passed along. And that is conduction. And it only happens in solids. It's really important. Although I've just noticed that is not how you spell the word solid. It's very bad. We'll call that our spelling and punctuation section there. It should be solid. There we go. But I'm sure you all spotted that instantly. It was just me that can't type, apparently. So that is conduction. Little note, bigger vibrations just means more heat energy. So the more something vibrates, the hotter it is. And when we talk about conduction, we have things that are good conductors and things that are bad conductors, and bad conductors we call insulators. So good conductors are most metals, and some specific examples are copper, aluminium, gold, silver. General rule, metal, good. Insulators, plastic, air, argon, rubber, wood, all these things are very bad at conducting energy through them. Most gases are particularly bad at conducting energy because their particles are really far apart, so it's quite hard for them to pass energy on. So that's conduction. Convection is next. Convection is what happens in liquids and gases. So when I heat up a gas or a liquid, they sort of expand and become less dense. So basically they rise. I'm sure you're aware of the idea that hot air rises, how hot air balloons work. So if I put like a piece of purple lump in there, you'll see what the purple lump is in class, but we're just going to say I'm just interested in this this little section of the liquid, and I'm going to heat it up. So as I heat it up, this bit gets bigger. It becomes less dense, so it rises. And as it rises, it moves up to the top, and then it'll get pushed away because there'll be more bits of water that are also getting pushed up that are being heated, and it'll get pushed over to the side. Now that it's over at the side, it's no longer near the heat, so it's going to cool down. Once it cools down, it's going to get smaller, it's going to get more dense, it's going to sink again. So we're creating this sort of current, this flow of hot liquid or hot gas. So that's why the liquid sort of goes around in this little loop here. It's just the flow of the heat as it rises, then it cools down and it drops and it just goes round because there's more and more particles doing the same thing. So that's convection. So next we've got radiation. Now radiation is different to conduction and convection because radiation doesn't require a medium. It doesn't require anything. It transfers through vacuums, goes through whatever is there. And it's really, really important actually because if radiation didn't work the way it did, heat from the sun wouldn't be able to get to the earth because there's a great big vacuum between us. So it's, you know, pretty important. So radiation is how all the heat from the sun makes it all the way to the earth. So whether things are good at absorbing or emitting radiation, so it's infrared that they're emitting, it's just heat energy, depends mostly actually on their colour. Dark or matte colours are very good absorbers and therefore also good emitters of radiation, whereas light colours and shiny surfaces are really good reflectors, so they don't really absorb the energy, they just reflect it off, it just bounces off and goes back where it came from. So, the thing people often forget is that good absorbers are good emitters as well. That's why if you're going to have a mug of tea, you're probably actually better having it in a white mug because your tea will stay hotter for longer. If you're going to have your cup of tea to try and warm your hands up, then you probably want a black one because it'll take the heat from the liquid into the black material, then the black material will also emit that to your hands. So, it's important when you're picking what type of mug you want for your tea. So, let's just have a little look at a thermos. So, we've got a thermos, it's designed to keep liquids warm. So, it's got a few important features. It's got a screw top, it's got a silver inner lining, and then it's got a vacuum between the inside lining and the outside lining. So what I want you to do is just pause the video for a second and have a think. How is the thermos good at keeping drinks warm? Try and use each of the ideas, so conduction, convection and radiation. Okay, so let's have a look at the answer then. So the lid prevents heat loss via convection because it stops the heated up air from leaving, because that would cause it to cool down. It just means that the heat, it still sort of moves around inside in the gap, but it stays inside the thermos. The silver surface reduces heat loss via radiation because it's just going to reflect all that energy back in. It's going to keep it inside. It's not going to let it radiate out from that inside container, because the inside layer is going to get warm, but I don't want it to give out that heat anywhere else. So by making it silver, it won't give out much heat. Then by keeping it in a vacuum, well, vacuum is an ideal insulator because we can't do conduction through it and there's no convection possible, so it stops the heat from going anywhere else. So thermoses work using ideas of all three, conduction, convection and radiation. So the important thing then is to try and talk about using these ideas for insulating our homes. So my word, I've had some horrible spelling errors in this one. I've no idea what double glousing is, but I was interested in double glazing. There we go. Corrected as we go. There we go. So double glazing reduces energy loss by conduction. The gap between two pieces of glass is filled with gas or contains a vacuum, so that stops the conduction from happening, so the heat stays in your home. Next is loft insulation, which reduces energy loss by conduction and convection, because the insulation prevents the heat from being conducted from the ceilings at the top of your house to the roof and then being radiated away. It just stops that from happening, so it just stays inside your home. Then we've got cavity wall insulation. So most walls, you've got 2 layers of bricks on the outside of your house and there's a gap in between, it's just filled with air. Now air is a good insulator, but because the air can move, you get convection currents. So what they do is they fill it up with foam, and the foam just traps the air. So we've still got that good insulating, so which stops the conduction, but now the air can't move, so it prevents the convection as well. Okay, oh, need to take my pen off so I can keep moving. There we go. Right, so after we've paid for this insulation, we need to look at how long it's going to take us to get our money back, because we're going to have to have spent money in order to buy this type of insulation, but the idea is it'll save us money on our heating bills. So this brings in the idea of payback time. And payback time is equal to the cost of the insulation divided by the annual saving, and that'll tell you how many years it is till you get paid back. In this instance, double glazing will pay for itself in 40 years, because I do 2,000 divided by 50, which gives me 40 years. But the draft excluder only cost me £10 and saves me £20 every year, so it'll pay for itself in 6 months. That's how they work. And you can be asked to calculate these. You don't need to remember these numbers, don't worry. These are just example numbers. But you would be asked to maybe calculate a payback time. Next thing we need to talk about is efficiency. And efficiency is a measure of how much useful energy you get out of the object. So how much of the energy that you put in went to do something that you wanted. So let's look at a TV. So this is my TV. I'm going to put in some electrical energy. I'm going to put in 200 joules. I'd get out 80 joules of light, which I want so I can see the picture. 40 joules of sound, because I want to be able to hear what's going on. And the rest will go as heat. So that's the wasted energy. So in the exam, the first thing they might ask you to do is calculate how much heat energy has been created. So how much wasted energy there was. So all we need to do is add up the 80 and the 40, which gives us 120. Then I put in 200 joules. 120 is useful, so here's my 120 useful joules. So however much is left is going to be my 200 minus 120, so that's going to equal 80 joules. And that's all you do. So that's the first thing when we calculate how much energy has been used usefully. So if I then want to calculate the efficiency, what I'd do is I'd put in the useful energy out divided by the energy in. In this case, that is the useful energy is our 120 joules, and we divide it by the energy that we put in, which is our 200 joules. Then we're going to times that by 100, and all you need to do is plug those numbers into your calculator, and you'll come out and you'll see that it's 60% efficient. So that's how we calculate percentage efficiencies. Again, you will always be given the equation, you'll just have to pick out the numbers and then plug them into the right place. So once we've looked at where the energy is coming from and going to, what often you get asked to do is to present the data into a sciecnce diagram. Basically a sciecnce diagram is just a big arrow showing where the energy is going. So I'll show you an example of one here. So let's say we've got a light bulb and it's running on 100 watts. So watts is just a unit of power, and it tells you how many joules per second that the light bulb is using. So it uses 100 joules per second in this case. 20 joules per second going to light and the rest going to heat. So we're going to draw this as a diagram. So I need to think about my input energy first. My input is 100 joules per second of electrical energy. So what I'm going to do is I'm going to draw the trunk of my arrow. And what I've done is I've made it so that it's sort of 10 blocks high. That represents the 100 joules, so each block represents 10 joules, just to make it easy. I then need to think, where is the energy going? So I'm looking at my output energy. So I put 20 joules per second into light. So I do an arrow that goes straight on, that's the light energy. And because it's 20 joules, it's going to be 2 blocks high, because the whole thing is 100. There are 10 blocks, each little block represents 10, so I need 2 to represent 20. So that's my energy that's going on, going forwards. Now the rest goes to heat, so that gives me 80 joules that is heat energy. And because that's not going on and being usefully used, we point it down like this to say that it's the wasted energy, and that'll just take up the rest of the width. Now, you don't have to worry about colouring it in or splitting it into blocks. What you do is you might measure, so this was 10 centimetres, this would be 2, then the rest of it would go down, that would be 8 centimetres going down. And we're just measuring the beginning trunk here when we do this. This is just showing you where the energy is going, but at the same time it's giving you a quantitative, so a numerical idea of exactly where all the energy is going and how much goes where. So that's the diagram. We'll do a lot more practice with the sciecnce diagrams because they're quite like them. They might seem a little scary at first, but they're pretty easy really. Okay, so that is the end of P1B. Remember, if you've got any questions, jot them down and ask me when you see me.